my name is Thomas. I'm working at the V Group in the business development for nanoimprinting, lithography, and wafer level optics. And today I will tell you something about nil and photonic integrated circuits. Yes, it works. Again, some very brief words about the company. So our business model is based on equipment sales. We are still fully family owned and have around about 1,400 employees worldwide. Our headquarters is in Austria, and we have fully owned subsidiaries in the US, Japan, South Korea, China, and also Taiwan. And this talk will focus also our nano imprinting lithography equipment. Short introduction about silicon photonics in general. So basically photonics, it's we understand again as the art of generating, manipulating, guiding and detecting light. The silicon photonics, it acts kind of a material platform to structure and use different materials, and the base for it, it's basically SOI wafers. And it's the motivation behind is really that the standard already existing processes can be used here in order to be quite cost effective. The most well-known use cases for silicon photonics are listed here. It's for sure 5G, data centers and communication, and we heard it also at the last talk from Sabik that this entire AI boom made the topic of power efficiency a lot more important. What you see also on the next slide, and also quantum computing, it's also very interesting for silicon photonics. Talking about power consumption, well, on the world, basically we have kind of a limit for our energy production worldwide. And the entire AI boom will not stop, and it's still scaling here. And somehow we will reach a certain limit where basically it's not economically anymore to spend more power on AI. That's why they need the entire data centers, and everything needs to be more efficiently. And that's where silicon photonics comes into play. And in general, we distinguish silicon photonics into 4 different key components. It's to create the light with the light sources. Here, most of the time, 3-5 integration, especially for bonding applications, is here quite interesting for us. You need to guide the light, you need to manipulate it, and at the end of the light path, you need to detect the single photons again. And with respect to nanoimprinting lithography, we feel most comfortable here on the packaging actually. So, for example, with edge couplers or also with grating couplers, where I will show you also later on some examples. All this story around silicon photonics comes with certain requirements, and we distinguish them basically in 2 different main categories. It's the technology, where it's all about to structure and pattern really, at least to have the possibility to structure and pattern here really arbitrary shapes at a very high resolution, so allowing really to have the exact copy of the master, for example, at a very high repeatability and pattern fidelity. And not only on the entire wafer, so it's also quite essential to have the possibility to structure only certain area of the wafers, and also to scale not only in area, but also in volume, so from small to high volume, and with the right material properties in case they are active materials and will stay permanently on the imprint. The other point is the integration, and there it's quite important that the entire process needs to be compliant to the standard semiconductor chain here, and again here the possibility to structure only on pre-selected areas on the wafer, and this goes along with the very precise alignment accuracy, what is required here if we want to imprint on a functional wafer, and also the precise control of of the residual layer thickness. And this basically is the know-how what is required, and it's all about the material, the equipment, and the process. And that's where we see nil quite essential here in the future, because nil is really, it's a cost-effective and flexible technology to enable here micro and nanostructures on wafer level in a single shot. And as you can see, the process here is actually, it's pretty simple. You just need a structured stamp here. You did some coating of the material on the substrate. You get in contact with the stamp and the substrate. You V-cure it, detach it, and then you can reuse the master again. The working stamp again, and we did already. So we did already some work here to set up here basically the ecosystem. So we have quite good collaborations with different master suppliers. At the same hand, we have a good relationship to different material suppliers in case of the different material properties. And for sure, we control also our internal processes in terms of the step repeat mastering, smart nil replication, also wafer level processes. And we can also scale here from R&D to fully automated HVM. And that's all accessible via our nil Photonics Competence Center, which acts here actually as a kind of an innovation incubator. So you don't need to have the entire infrastructure at your facility. We can really do here the process development and also the entire characterization of the results later on. Our key market for nil actually, it's I talked already before in the talk, so it's AR/VR, wafer level optics, and this focus again of the talk, it's about LiDAR and silicon photonics. Again, with this very flexible possibilities for wafer level optics and smart nil replication in terms of the structure height. And how does the process look like? So we can distinguish here between the working stamp fabrication and the imprinting process. The working stamp fabrication will be utilized then on the imprinting process, and one of the key differences is here really that on the imprinting process we can also utilize inkjet coating, for example, to really to have the possibility to coat and structure only certain areas on the wafer, what is quite important if you have a functional wafer and you don't want to structure the entire wafer. Some use cases where we exactly did that, this partial imprinting, was, for example, with an Israeli company called Terramount. Here we did some edge coupling actually. So we imprinted here really in this 20 micron deep trench, and we imprinted here this micro mirror actually, and also a photonic bump. And this photonic bump, it's used as a passive alignment module, basically a passive alignment structure to get really a high efficiency of the coupling. Another very, very nice application was in the field of automotive for LiDAR applications, for example, because the entire boom, hopefully the entire boom on autonomous driving will increase the need also for LiDAR devices, but at the moment they are still quite bulky and for sure not nice to look at. And also still this Waymo cars, the fully autonomous driving cars, they have some quite bulky optics on top of the car. But on the final roadmap, it's basically it's the requirement to integrate the LiDAR basically inside the front lighting. And here, we heard it also yesterday that the automotive industry, they're actively looking for a solution and processes from the semiconductor industry. And yes, we can really act here as kind of a bridge here to connect here those two worlds, and it's happening more and more. And what we did here with respect to a LiDAR device was actually in a European funded project called Tinker, where Marelli was actually the use case provider, because they had the idea to miniaturize a LiDAR and to integrate it into the headlamp. And what we did here, we imprinted here some grating couplers with an active high refractive index material from Inctron on a silicon photonics chip. And again, we had the story about this very high alignment accuracy. We had the story of the residual layer thickness control, of the exact pattern fidelity after replication. And so we were really able to fabricate those waveguides with our nil technology here. And the outcome of the project was also kind of a process design kit, how to design the waveguides for this light application. That was basically the output here. Well, just some words about our competence center. So we can really give you access here to the entire manufacturing chain of doing photonic elements here. We have quite a huge clean room space available with 1,300 square meter. Also still expansion is here ongoing. So inside the clean room, we also integrated quite a huge metrology area. So we can really ensure you here quick turnaround times for certain for the processes, and to get also the validation for the of the metrology, and also for sure we can do also the entire reporting, and we can really help you to ramp up your ideas here. Thank you.